So, you're doing continuous time random walks, right? And the basic thing, just to recap, was the fact that we have some sort of a jump distribution, jump PDF, which in principle tells us how long do I need to wait before I make the next jump, and what is the size of the next jump, x and t. And in general, we were looking at the decoupled case, where you have these two distributions as independent with some distribution of jump sizes lambda of x and some distribution of waiting time intervals w of t, right. And then we said showed that if you work in Fourier Laplace space, ultimately what you want is the probability distribution p of x t, right. And if you work in Fourier Laplace space p tilde of k comma s, you can express that as long as these are decoupled in terms of the Fourier transform of the spatial probability and the Laplace transform of the waiting time probability, and that gave us something which was this 1 minus w hat of s by s, right, and then 1 by 1 minus w hat of s lambda tilde of k, right. So, in principle, if you know these two distributions, you can get this Fourier Laplace transform, and then you can do an inverse Fourier inverse Laplace to get what is the probability distribution. Now, we talked about the Brownian motion or the diffusion limit. Brownian motion, right, where we said that if your waiting time distributions are exponentially distributed, so 1 by tau e to the power of minus t by tau, while your jump distributions are Gaussian distributed, so 1 by square root 4 pi sigma square e to the power of minus x square by 4 sigma square. You can show that what you get for this p of x is you get back your Gaussian. So, if you combine these two, you get back your Gaussian p of x comma t, which was 1 square root 4 pi sigma square t by tau, the mean time e to the power of minus x square by 4 sigma square t by tau, right. And further, we calculated the moments. So, let me just write down the moments. The moments of the distribution m and s was minus I to the power of n dn dk n, right, of this p tilde of ks, of this p tilde of ks, right. And then for the second moment, if you do this, if you substitute what you have over here, these are evaluated at k equal to 0. For the second moment, if you do this, you get m2 of s, which is essentially the average x square, but in Laplace space is w hat of s s1 minus w hat of s L square plus 2, right at the bottom. So, I have some space, plus 2 w hat of s whole square by s1 minus w hat of s whole square average of the square, right. So, this was for the second moment, where this L's are the single step mean and the single step variance, right, obtained from purely this lambda of x. And then if you substituted this exponential plus Gaussian distribution over here, what you get is average x square of s. So, for this process essentially this is a general thing, you get something like average L square by S square tau, and then if you do the inverse Fourier, this gives you x square t is 2 sigma square by tau times t, which is like your 2 times diffusion coefficient times t to the power of 1, right. So, this is what we have. Is this clear? So, this was the scheme that we have, and this is a sanity check that if you put back sort of Poisson distributions and then Gaussian step lengths, you get things, you get back diffusion. Now, the thing is to get anomalous diffusion out of this, and that has to do with the choices of these waiting time distributions and this lambda of x, right. So, that is the aim, to get anomalous diffusion. So, I will do a few cases, but mostly I will keep it because the calculations are fairly long. So, I will just indicate the calculations because doing it would actually be quite a big thing. So, the first case, so here remember what we said was, for this case I have both a mean time and a mean variance, right. In the, when I have these two probability distributions, I have a mean time which is tau and a mean variance which is sigma square. So, you get different, and we had said that you get different cases of the CTRW depending on whether both these quantities exist or not. So, we consider one case where you take essentially long rests, and this gives you subdiffusion. So, this gives you subdiffusion. What does that mean? So, that means that I take a waiting time distribution which, instead of being exponentially distributed, is now power law distributed. Okay. So, I take something of the form like tau by t to the power of 1 plus alpha, okay. Which means, because I now have a power law, there is a finite probability for these waiting times to be very large, right, as compared to the exponential. Okay. So, that is what I mean, that is what is meant by these long rests, that occasionally once in a while with some finite probability you will have very long gaps between these hops. So, that is a long rest, okay. And you will have some some normalization in front, and I take alpha between 0 and 1, I take alpha between 0 and 1, okay. Now, of course, if you do the mean time, mean waiting time according to this distribution, it is, so if I do t, which is integral t wt dt, this of course diverges, right. So, this thing diverges and therefore, there exists no mean time for the power. So, this is one category where this mean time diverges. So, we can let the other thing be as it is. In fact, you can take the same Gaussian lambda of x, which is 1 by square root 4 pi sigma square e to the power of minus x square by 4 sigma square. And in okay, so for this w of t, you can actually do the Laplace transform, and you can show that the Laplace transform of w of t, so w hat of s is 1 minus s tau to the power of alpha, something like roughly like this, up to constants. So, if you have 1 by t to the power of 1 plus alpha, if you work out the Laplace transform, you will get 1 minus s tau to the power of alpha. And this, of course, this one anyway we know, the lambda, what was I saying, lambda tilde of k is just exponential of minus sigma square k square. So, it is not normalized per se, it has some constant in front. So, let me see. Yeah, so this A alpha one can put certain things which satisfy certain properties. Let me see. Yeah, it's anyway. So you're right. So this A alpha is not really a normalization constant; it's some constant. People traditionally choose some forms which are gamma functions for particular reasons, but let me not get into that. It's just some tau by t to the power of 1 plus alpha. Okay, and so there's something in front, whatever. But that has Laplace transforms of this form. Yes. Which one? This one? Yes. So it's not a one step calculation. This is a mathematical thing which I also don't know. There are proofs called Tauberian theorems. There are proofs called Tauberian theorems which talk about the Laplace transforms of quantities like this. And it has certain assumptions and certain special conditions in which you can show that the Laplace transform works out like that. Even actually this paper does not, this review paper also does not have it. There is a book which works, if you are doing the full Laplace transform, there is this book by Klafter which has the details of this. I have to see what is the name of the book. First Steps in Random Walks, Klafter and Sokolov. First Steps in Random Walks. That has more details about these calculations. So, which is why I say I am skip jumping a lot of it. So, a lot of it is perhaps not foolproof. But if you go back and look at this book, they have much more detailed proofs for each of this. For now, assume that you can have a Laplace transform which is defined in this form for a power. So, also this power law, technically you need not have this throughout T, as long as the asymptotics long T behavior is like this, that suffices to have a Laplace transform like that. The short time behavior can be of different forms, but at least so essentially the thing is that it should be a heavy tail distribution. So, you should have some sort of a heavy tail where you have an appreciable probability for long waiting times. Okay. Anyway, so in principle one can do these Laplace transforms, and then if you have this lambda of x, you can calculate this. Once you have both, if you assume both of these are true, you can substitute that over here in this p tilde of k of s, right, and that would give you something. So, if you work this out, if we work this p tilde of in the Laplace Fourier Laplace space, 1 minus w hat of s is just gives me this s tau to the power of alpha, s tau to the power of alpha divided by s, and then I have 1 by 1 minus this, which is essentially s tau to the power of alpha plus sigma square k squared to leading order, right. And again, in principle, this can be inverted to get what is this p of x comma t. It's again not a trivial inversion, but there are standard tables. It gives you something called Fox functions. It gives you something called Fox functions, which I'm not even trying to write down. But in principle, you can have this p tilde ks. And once you have the p tilde ks, it is possible from standard inverse Laplace and inverse Fourier tables to sort of get a closed form solution, and it comes in terms of the special functions called Fox functions. All right. What I want to look at just for the time being is this second moment x square of s. Okay, an x square of s. Again, remember for the spatial jumps, I have chosen Gaussian, which means that my average L is 0. And my average L square is just 2 sigma square. So, as far as the x square s is concerned, it is just this term that is relevant. So, if I calculate the second moment x square of s, this gives me this thing w hat of s. So, 1 minus s tau to the power of alpha by s into s tau to the power of alpha times L square. And again, one can do the inverse Laplace of this, and if you do the inverse Laplace of this, this gives you x square as a function of time, right? And the leading order is just 1 by s to the power of alpha plus 1 t to the power of alpha. So, this gives you a t to the power of alpha, and then a coefficient which is roughly like 1 over tau square. So, this is by tau square, and then of course, there is an average L square sitting down over there. So, if I and maybe other constants sitting in front depending on, but roughly if you work out the MSD, you get something which is of the order of t to the power of alpha, where this alpha is between 0 and 1. Okay. So, essentially what this leads to is subdiffusion, subdiffusive transport, and essentially you are saying that this is a limit where instead of following this Poissonian waiting times, I follow this heavy tail waiting times. The fact that I am taking these long rests between jumps ensures that my transport is slower than the diffusive limit, and it's related to the exponent is related to the form of the waiting time distribution that you choose. Okay. So, this is one case where your jumps are finite, but your waiting times are infinite, or the mean waiting time is infinite. You can do the opposite case where your mean waiting time is still finite, and you can take it to be Poissonian, but you take the jumps to be now power law distributed. Okay. So, now you have a finite probability for very long jumps. Okay. So, that is called Levy flights in generically. So, that was long rests. This is the opposite thing, long jumps. These are called Levy flights. Okay. So, here what you do is that you take a jump PDF lambda of x, which is now power law distributed. So, it is some mod x to the power of 1 plus mu, again asymptotically, some constant in front, sigma to the power of minus mu and something else in front. Okay. It's in this regime. So, again, instead of having Gaussian jumps, you now have power law distributed jumps, which means that you have some finite probability or appreciable probability for making very long jumps. But you can say that the waiting time is still Poissonian. So, 1 by tau e to the power of minus t by tau, which means that the mean waiting time exists. In this case, of course, the mean the variance does not exist because that diverges. Okay. And this of course had this. As far as the Fourier transform go, you can show that the Fourier transform of this sort of a function, this power law distributed jump lengths, goes as something like exponential of minus sigma to the power of mu mod k to the power of mu. Okay. So, for the Gaussian, remember this was like minus sigma square k square. Here when you have this sort of a power law, it goes as sigma to the power of mu, k to the power of mu, and this is of course w hat of s is 1 by 1 plus s tau. This is my standard Poisson. Now, in this case, again you can write down the Fourier Laplace transform P tilde of Ks using whatever formula we had, and that gives us again gives us tau by S tau plus sigma to the power of mu mod k to the power of mu. Or in general, therefore, this is like S plus some k alpha, sorry, some k mu mod k to the power of mu, where this k mu is this sigma to the power of mu by tau, is like a generalized diffusion, generalized diffusion. So, if you remember when we were working it out for Brownian transport, what we got here was 1 by S plus d times k square, 1 S plus d k square, and that therefore, the coefficient of that k square term was our diffusion coefficient. In this case, you get something like S plus k, some constant k times k to the power of mu, where k mu, this constant has this sort of a form, and it's generally called as a generalized diffusion coefficient. Anyway, again you can invert this to find out what is p of x comma t. It's some, again, very complicated form, doesn't matter, but if asymptotically at least one can write down that this has the form p of x comma t, asymptotically has the form k mu t by mod x to the power of 1 plus mu, 1 plus mu. And if you use this to calculate what is x square, the MSD, or if you put in this MSD into the formula for the second moment, x squared of time, this thing is actually infinite. Okay. So, this thing diverges. So, if you have a scheme like this, where you have a power law distributed step lengths, so infinite variance, but a finite mean time, and if you follow through the procedure after whatever mathematical difficulties there are, you can show that the MSD in this case, average x square of t, is actually infinite instead of going a super diffusive, which is what one would have liked. But people work around that. So, you can calculate, instead of this x squared t, you can calculate what are called fractional moments. So, you can calculate average x to the power of delta, okay, this quantity. Instead of calculating x squared, you can calculate x to the power of delta and show that this goes as t to the power of delta by mu for delta less than mu less than 2. Okay. So, mu is anyway less than 2, and delta has, if delta is less than mu, then you can calculate this average and show that this goes as t to the power of delta by mu, which means you can calculate some sort of an MSD, you can define some sort of an MSD x square something box, which is this average x to the power of delta, this quantity to the power of 2 by delta. Okay. So, it gives you some sort of a square, okay. And that would be, so that goes as t to the power of 2 by mu, therefore, since x to the power of delta goes as t to the power of delta by mu. And this quantity, of course, so since mu is less than 2, this quantity t to the power of the exponent is greater than 1, which is something like a super diffusion. Okay. But the actual MSD, this proper MSD is of course infinite. And it is infinite in some sense, because what you are doing over here is that you are allowing very long jumps, because you have this power law, tail, but your mean time is still finite, right, which means that essentially for physical particles, if one thinks about motion of physical particles, what you have is infinite propagation velocities. We can make very long jumps in a finite amount of time t. So, therefore, this MSD in that sense. So, this is somewhat unphysical. This is somewhat unphysical, at least in real space, because it implies infinite propagation velocities. And this MSD blowing up is a sort of signature of that. So, you can do long rests, that gives you subdiffusion, but if you do long jumps and finite resting times, you get something which is not very well behaved. Some quantity behaves like superdiffusion, but the proper MSD does not. And the way to people rescue it is to say that, well, I will not have infinite jumps, I will not have instantaneous jumps, but when I make a jump, I will have some time penalty associated with it. Okay. So, if I am making a very long, if I am here and if I am making a very long jump, I will spend a time making this jump that is related to how far I have jumped. Okay. Which, what does that mean essentially? What that means essentially is that there is a relaxation of this assumption we had made that this lambda of x and this w of t are decoupled. Okay. You have some w of t and you have some lambda of x and they are decoupled. If you have to do this properly, then one takes a coupled sort of a form. So, one takes a coupled jump PDF, okay, where you say something like this, that I have psi of x comma t, right, and I want to make long jumps. So, I want to do something like x to the power of 1 plus mu. Okay. So, I want to have long jumps, but now the time, the waiting time distribution that I have depends on this jump size, and that people implement in different ways. So, one way is to have this, that I have this power law for the jump, and then I say that the time that I spend doing this jump is related to how much I have jumped through some relation like this, x minus t to the power of nu. I think that is this is actually written as mu instead of 1 plus mu. So, x minus. So, this is a coupled jump PDF where you no longer have instantaneous jumps, but you penalize how much time you spend for these long jumps. And in this case, of course, the maths has to be changed a bit, so which is why again I am not working it out. But you can show that there are different limits. For example, so in this case, if you start with this jump PDF, you can show that in certain cases your x square of t, depending on what this mu is and what this nu is and so on, you can get finite x square of t. So, you can get finite MSDs, and these MSDs, for example, so one thing is that if you have a mean time between jumps or not. So, if you have a mean time exists, the condition for that is nu into mu minus d plus 1 is greater than 2, where d is the diffusion, d is the dimensionality of the walk. So, this is, I was writing in one dimension, but in principle you can write in any dimensions, r minus d power mu. So, d is the dimensionality of the walk, and you can show that the mean time exists if this nu and mu and d satisfies this relation. And if this exists, and further if this thing is nu into mu minus d minus 1 is less than 1, then you will get the MSD x square as a function of time as t to the power of alpha with alpha greater than 1, which is super diffusion. Okay. And again, this alpha I can write in terms of this news and these. Or again, if the mean time diverges, it does not exist. If the mean time diverges, then you can show that this MSD x square versus time and up to certain conditions. So, this is if nu into the same thing mu minus d minus 1 is less than 1, then you can show that this goes as t to the power of 2 nu, and therefore, that is super diffusion if this nu is greater than half and subdiffusion if this nu is less than half. So, if you have this sort of coupled jump PDFs, then you can get depending on what exponents you choose, you can get super diffusion and subdiffusive behavior in principle from a similar formalism. These are called Levy walks. So, the Levy flights are things where you do not penalize long jumps like time wise. The Levy walks are walks where you actually penalize how much time you spend in making these long jumps. Okay. There are different implementations of this. So, for example, one implementation is let me see. So, this is one probability. There is another implementation which is again Levy walk, which is coupled again. So, psi of x comma t is like power law distributed times so 1 by t to the power of 1 plus alpha, okay. And then how much you jump depends on how much time you have waited. So, this goes as x minus c. So, it says that you choose jumps from this sort of a power law distribution, but how much you will jump depends on how much you have waited, and it is sort of a mental picture that you are moving with a velocity v in this waiting time. So, v of t. And again here it works. Here you have these two things mu and nu. Here you only have this alpha, and in terms of this alpha you can show that this x square of t goes as t square if alpha is between 0 and 1, t to the power of 3 minus alpha if alpha is between 1 and 2, and as t if alpha is greater than 2. Okay. So, you get ballistic transport, which is t square. You get super diffusive transport if your alpha is in this regime 1 less than alpha less than 2, and if your alpha is greater than 2, then you get diffusive transport square goes as t. So, this is how in general when one is trying to model these sort of anomalous diffusion, you choose these jump PDFs appropriately, often with some background idea of what the process is and how you are making these jumps. But yeah, so once you do this, one can show that you get anomalous diffusion in various contexts through this sort of a formalism. There is, like I said, there are different other forms. So, this is the CTRW formalism, but I do not have time, but in general one can write down master equations corresponding to this CTRW or Langevin equations or Fokker-Planck equations. The mathematics of that is a little complex, but in principle one can do all of this machinery that we introduced for cases like this. It's just that, for example, when we are writing down the master equation, if you remember, something like del P del T was sum over states. So let me call it P of x comma t, P of x prime comma t, and then W of x to x prime. So this is summed over all x prime minus, so this was the gain term, and then there are loss terms. So omega P of x comma t, where this I was writing from x prime to x, so from x to x prime, right. So my general master equation, so my master equation that I had written down earlier had this form, where these omegas were transition rates, right. So these were the transition rates. When I say this was a transition rate, at the back of our mind, what we have is that, so therefore these are units of inverse time, right. And therefore what this means is that typically I am thinking of Poisson distributed waiting time distributions, where I have some time scale associated with these jumps, and then I input that time into these rates. So the inverse of those times gives me the rates, right. But if you no longer have these sort of Poisson distributed waiting times, but you have these complicated waiting times, power laws or whatnot, then in general you cannot write it in this form, but you have to write some full, x prime, t prime, and then x t. So what is the time difference and what is the space difference, and then these will be related to these jump distributions. So these are called generalized master equations. So in general, so these are called generalized master equations, which I am not getting into, but all of this formalism that we did in principle can be carried over to these sort of anomalous diffusion models as well. Okay. I wanted to mention something else. Right. So I wanted to mention an example, which is something we are sort of thinking about now. So like I said, so what sort of a jump PDF you take depends on what is the biological or what is the process that you are trying to model, and therefore what sort of biology you have in mind. So since we've talked a little, let me just give one example before I end. Which is that, remember, we are thinking of our protein search problem, since that's something we have worked out, protein search problem, where you have your DNA, these are your DNA bases, and you have some protein which is performing a search along the DNA backbone, and then it could unbind and do this 3D search. It could do a 1D search, and then it could do a 3D search, right. So this is what we can work out. But in principle, of course, this DNA that you have is a polymer. So this DNA is some sort of a polymer, right. So therefore the backbone on which the protein is doing this work is not a straight line. It is something which is a polymer, and therefore let us say a protein is here. It is doing 1D, 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 1D. It comes over here. It could now, of course, do 1D along the backbone, but it could also do 1D along this sort of Euclidean distance. So if it has some polymer segment which is next to it in 3D space, it could hop there as well in principle, instead of following the backbone, right. So that would be a long jump along the backbone, but a short jump in Euclidean space, right. But along the backbone, if you ask how these contacts are distributed, like how often does a polymer approach each other, or how does that probability go, that essentially this is a probability that if you have two base pairs separated by some distance s, what is the probability they come in contact? And that one can work out the polymers theory and show that that actually goes as some sort of a power law, some s to the power of alpha, let us say. Depending on what sort of a polymer model you take, whether it's self-avoiding or self-interacting and so on, you can work out what this exponent will be. But now if you're thinking about this protein and you're saying that it jumps to nearby base pairs, whether that is nearby along the backbone or along the 3D space, what that means is that in addition to these jumps, it also does these long jumps where these long jumps are distributed according to this power law. And that would give something which is technically not diffusion, which would give, for example, anomalous diffusion. So, that would be search processes that are facilitated by anomalous diffusion by these long jumps, which reflect the contact space probability of this polymer. Okay. So, this is just an example of, depending on what sort of a problem you have, one might choose different sort of jump PDFs motivated by the biology. So, I think I will stop here for today. Sorry, I will stop here for the course.